You're not rid of me yet, because I'm just going to sit in the technology panel.
So yeah, now we have something completely different. We've had a lot of wonderful talks this week. But now we're going to change pace a little bit, and we're going to do a 30-minute panel discussion with some of the researchers and engineers from around the globe that are continually pushing boundaries in our field. So I'm going to introduce our panel once I get my slides up. If I can figure out how to do this. Okay, so the first member of our panel is the esteemed Sebastian Haffert.
Should I just sit down? Or?
Yeah, just sit on the other end. And then there's Dan Sirbu from NASA Ames, Eva Laginja from Lagrange OCA CNRS from France. We have Naoshi Murakami from the Astrobiology Center in Tokyo, Japan. Rob Van Holstein from ESO in Chile. We have Daniel Shanks from NASA JPL, and Brianne Sitarsky from NASA headquarters / Goddard Space Flight Center. And I'll be the moderator. I'm Gareth Ruane from NASA's Jet Propulsion Laboratory here in Pasadena. So I'm going to ask our panelists to do 1-minute introductions. We'll go in order from furthest to closest. So let's take it away. So Sebastian, everybody knows. So you don't have to touch the microphones, by the way. They're just on. They're hot, so
okay.
No side comments either.
Well, I just gave a talk. You might have seen what I work on. Well, you can see I got my PhD in 2019, Light Observatory, moved to University of Arizona as Hubble Fellow and a postdoc. And since 2024, I'm now assistant professor at Leiden Observatory.
I'm Dan Sirbu. I'm a research scientist at NASA Ames. I serve as the PI of Astropic, and Rachel gave an excellent presentation earlier this morning summarizing the latest results, the architecture. I also serve on the Roman CPP, where I'm interested in enabling new modes that will enable Roman to perform additional capabilities and do additional science, such as imaging binary stars. You may have seen Eduardo Bendek's poster here at this conference that covers that. And before that, I started as an MPP at NASA Ames and stayed on since then. And before that, I actually did my PhD at Princeton working on star shades.
Hi, I'm Eva. I'm an associate researcher in France, in Nice, as of this past Monday. Before that, I've been a little bit everywhere. So I've worked at Space Telescope Science Institute for a while. Before that, I did my master's in the Netherlands. Now I'm in France. I'm an original of neither of these countries because it came up this week. I have a background in looking at how we can optimize or how to better understand segmented telescopes for all the topics that Sebastian touched on in his talk. I'm currently very active in the Roman CPP together with Dan and a lot of other people in the hardware working group because we want to understand how to pull out the best possible performance out of Roman CGI with what Roman is flying. And one of my main work touches on testbed demonstrations of a lot of different technology for chronography and wavefront sensing and control.
You don't need to touch it. It's already on.
It's on.
Oh, yeah.
You don't need to touch. Yeah.
Hi, my name is Naoshi Murakami from Astrobiology Center in Japan. So I received my PhD from Hokkaido University and work as a postdoc in NLJ for several years as a member of the Stellar Interferometer project called MIRA. And after that, I moved to the Hokkaido University back again. And I'm working on the new technology about the wavefront sensing and control, as well as the development of the phase mask chronograph based on the photonic crystal. And we built 2 laboratory test beds in Hokkaido University called EXIST and FACET. Here is a picture of the EXIST. With great support from the young student. And now I'm working at the Astrobiology Center, and my main task is the technology R&D towards the Habitable Worlds Observatory.
Hi, I'm Rob van Holstein. I'm a fellow at the European Southern Observatory in Chile. I got my PhD at Leiden Observatory, actually around the same time as Sebastian. My work focuses on high contrast imaging and especially on polarimetry. And I primarily use SPHERE. And what I try to do is to push the high contrast imaging polarimetry as far as we can. And for this I've worked on theory like polarization aberrations, calibrations, data reductions, observing techniques, but also actual observations and interpretation. And yeah, it's there. So one of the, well, I think one of the examples here is, for example, the detection of very small polarization signals on the planetary mass companion of DH Tau B. I think that's a nice example of this, how we try to push the polarimetric information that we can get out of the data.
Hi everyone, I'm Dan Shanks. I got my PhD from the University of Arizona in 22, doing absolutely nothing that has to do with astrophysics or coronagraphs. And then I got to JPL as a postdoc, and I had a lot of experience in nanofabrication. So my job at JPL is making custom optics using semiconductor cleanroom tools, a lot of grayscale lithography. Think the type of optics that went on the focal plane masks for Roman CGI. Those are the type of custom optics that I make. And for the past couple of years, as a micro devices engineer, I've been working on metasurface technology for polarization aberration correction for HabWorlds.
Hi, I'm Brianne Starsky. I'm the Deputy Principal Architect, which is a mouthful, I know. Deputy Principal Architect of Habitable Worlds Observatory. I'm at NASA Goddard and at NASA headquarters. Prior to that, I was the optical systems scientist and deputy project engineer for the Giant Magellan Telescope, so I have that synergy between ground and space. Prior to that, I did a very short stint in defense, realized that wasn't my thing, and went back to astronomy. And I got my PhD in 2016, cutting my teeth on the Galactic Center, astrometry, and also working with Mike Fitzgerald on PSF reconstruction.
All right, thank you. So I'm going to ask the same question first to each member of our panel. So starting with Sebastian and working our way back now, I want to ask, in your technical career so far, what work are you most proud of?
What work am I most proud of? What I would say is that what the thing is that I'm most excited about is the fact that I was able to dig a dark hole on sky with MagioX through the turbulence. I think that was really like the first time that worked. That was amazing. We celebrated quite a bit when we did that.
All right, go ahead, Dan.
So AstroPic project is what I'm most proud of. We've been able to go from theory, from optimal chronograph theory, manufacturing the devices, and now digging dark holes on chip, and continuing to do this with system-level demonstrations. So I'm very proud of the progress that we've made with AstroPic. And I'd also like to mention a separate project, binary star imaging. We've demonstrated multi-star wave control at OMC in vacuum at contrast levels very similar to what will fly in Roman. So we hope to be able to also demonstrate that and observe on sky with Roman.
Go ahead.
What I'm really happy about is that all of the investments I've started doing from very early on in my career that were around the testbed work, specifically for how to efficiently use those testbeds, not just for one-off ideas, have paid off in the long run. So for example, when you look at the amazing work that we've done on HiCAD over the years, we've done some incredible results, but because we've invested a lot with the team on there in making those results repeatable, investing in the infrastructure and investing in the people we trained, we managed to spin up very impactful collaborations with the THD2 testbed in Paris. Now I'm adopting a new testbed in Nice, the speed testbed, of which Remy also showed some early results. And so I'm very proud of the fact that these early investments that sometimes were side-eyed as maybe a waste of time are completely paying off. And we're also seeing how this is going to benefit Roman, and in the long term, I hope also HWO.
So the work that I'm proud of the most I don't think there is, but the contribution of the to the Roman chronograph as a member of the JAXA team. So actually, I was in charge of the fabrication of the substrate, highly polished substrate for both chronograph masks, both hybrid Leo and shaped pupil chronographs. So I don't think that my contribution is very large, but I'm very happy and I'm very proud to be to have been the, part of this great mission of the Roman chronograph.
So for me, the work I think I'm most proud of is the detection that we made of the polarization of DH tau B. Not necessarily because of the detection, but more because of all the work we had to do before this. So this detection was made with the near-infrared arm of SPHERE in the polarimetric mode, in ERDIS. So when SPHERE was designed, this polarimetric mode was not actually a real priority. There were other priorities, especially in finding planets. And so when it arrived actually at Paranal for commissioning, the idea was to just let's see if this works somehow and whether we can reach, I don't know, measure polarizations of several % in degree of linear polarization. Then actually by taking calibration measurements, creating full end-to-end Müller matrix model, pushing the observation techniques, data reduction methods, all these things was really an investment of years and years. We were finally able to actually get a polarimetric accuracy of far less than 0.1%, which then enabled these detections. And I think that's, I think it was a nice effort from a lot of people that really paid off.
So I would say a lot of the metasurface work that I see in papers right now is kind of proof of concept work, showing there's this new thing that metasurfaces can do, and there's not a lot of rigorous engineering that goes into these proof of concept papers. And I think at JPL we've done a pretty good job of starting the work of moving this metasurface technology from kind of a proof of concept phase to a fabrication tolerancing, work to the point where we can really do something with it with an error budget.
In order to achieve the 10 to the minus 10 contrast that we need in order to image and characterize Earth-like planets around sun-like stars, we need a very ultra-stable test bed or an ultra-stable telescope. And in order to ensure that the telescope is stable, we need a test bed in order to qualify the mirrors and so on. And so I'm the PI for that at Goddard. And we recently, just before the HWO 25 conference, actually were able to measure single-digit picometers, which is really insane when you think about it. And so I'm extremely proud of my group for being able to really enable those measurements.
All right, thank you. So we have a few more minutes of questions from me, and then we're going to open it up to Q&A from the audience. So I'll start with Rob, since you were the most excited to be part of this panel. So you have a good deal of experience with polarimetry and spectropolarimetry from the ground, especially on VLT. What role will these methods have in the ELTs, and how important is it to enable on a future space telescope like HWO?
Yeah, so I think I would like to, okay, so of course with polarimetry we can do basically two things, right? That's image and characterize circumstellar disks, and also image and characterize planets in reflected light. Now, I'm actually quite disappointed that on the ELT, the European ELT, the first light instruments do not include polarimetry. Personally, I think that's a mistake. If we see all the cool images that we get out of SPHERE, of GPI, Skexio, etc., I think it's a shame. But luckily, of course, on the GMT, we have the first light G-MegaOX, so I think that's, I'm very excited for that. And then hopefully later for PCS, and we know for Roman CGI and Habitable Worlds will have polarimetry. Now, I always repeat to people that we should not forget polarimetry. Don't leave it to the end, right? We know that if we add polarimetry later, we can do it, we can fix a lot of things, but if, for example, on Habitable Worlds, we want to actually detect a planet, we should take it into account from the beginning. Now, there's two things we can do with this. One is we can, of course, characterize an exoplanet, right? When we talk about an Earth-like planet or maybe find biosignatures, we talk generally about detection of, for example, oxygen in the atmosphere. But what's also important is to actually characterize more of the planets. And with polarimetry, we can do that. We can figure out more about the constituents of the clouds and also of the surface, actually, of the exoplanet. Is it water? Is it land? These kind of things. So it actually gives a lot of additional information. And on the other side, what also should not be forgotten is that polarimetry can actually help to increase the contrast. So what we show, at least in the ground, is that by doing differential polarimetric imaging, we can increase the contrast by 2 magnitudes, so by a factor 100. Of course, now we're only sensitive to polarized objects. But these reflected light planets, they're 10%, 20%, 30% polarized. So what you do then is that this planet, by using polarimetry, now the planet becomes 10 times fainter, but your contrast becomes 100 times better. So this actually may, at some point, make a change on whether we can detect the planet or not if we use polarimetry.
So Dan, given how important polarimetry is, what new possibilities might metasurfaces unlock for this application?
Yeah, I mean, the idea of a metasurface is you can apply an arbitrary polarization-dependent phase front, which means you can make a lot of interesting optics. There's already been a lot that's done with liquid crystals, but we can think about making metagratings. We can think about doing all sorts of fun polarimetry like that. And where metagratings really shine is the fact that you can combine polarizers and gratings into single optics to make compact systems for satellites and places where swap matters.
Naoshi, I have been following your work for quite some time on photonic crystal technology. What are the advantages that photonic crystals might bring to this area to enhance future instruments?
Yes, now we have been developing the coronagraphic phase mask based on the photonic crystal technology. So the one advantage of the photonic crystal is the fabrication defect can be made very small with an order of submicron, several hundred of nanometers. So based on this technology, we are now developing the discretized vector vortex, which provides only 2 phase values, only 0 and pi, like the 4-quadrant or 8-octant phase masks. So, for such a design, the planetary throughput becomes very high, and when the planet is just exactly the appropriate position between the phase transitions. So thanks to this advantage, we expect that our approach can enhance the coronagraphic performance for the future instrumentation, including the Habitable Worlds Observatory, which is especially suited for the spectral characterization of the exoplanet with known positions.
Okay, let's open it up to some Q&A from the audience. So if we have mic runners, we're opening up questions to any of the members of the panel. Ross, why don't you go first? You have a mic already.
Sure. Ross Belko, NASA Ames. Thank you for all the fascinating answers. My question, and I guess that might be for everyone, is what do you think would be the most impactful breakthrough, game changer technology, for astronomy in the next decade or two, and why?
Who wants to take it first? Probably someone who doesn't.
So I can take that. I think astrophotonics, we're already seeing the impact that it has on miniaturizing photonic instrumentation. It has a great deal of potential for HWO in order to make compact instruments that have additional capability. We're seeing that HWO studies are seeing that we may need something that's minibus sized in order to be able to cover all the channels, get all the full spectral bandwidth coverage. And so photonic integrated circuits and allows us to miniaturize the chronograph and be able to really add a lot of capability. And not just volume, but also in terms of being able to get higher science yields and more aggressive inner working angles.
So, did I also answer that question, or?
Oh yeah, sorry, that question was for everybody.
Ross said, I actually think it's GPUs. All the work that we're doing on the ground and for space and for manufacturing, for design, it all depends on GPUs. GPUs have really been the enabling technology for us to do high-speed wavefront control, to do this telemetry-based post-processing that I think is going to be the future. It's GPUs is enabling it. The design of meta surfaces, the inverse design of photonic devices, it's all enabled by GPUs. So I think it's actually the development of GPUs and data centers that is underpinning like the development that we're doing now, like all the development that we're doing in high contrast imaging. That's what I think.
Does anybody else have a burning answer? Our next question. Okay, let's move on to the next question then.
Hi, Miles Lucas, University of Arizona. In a decade or two, we're going to have ELTs with high contrast instrumentation really pushing the field in a major way. At that point in time, what will be the role of 10-meter class high contrast instrumentation? What will spheres, GPIs, SKEXEOs be doing while the ELTs are operating?
Eva, do you want to take that one?
Sure, I'm the person who has the least ground-based work, I think, at this table. I think one answer to that is I really want to point out Maisa's talk the other day. Like, we have seen that Keck has been around for a long time, you know, way longer than my career, for example, but it has been using a segmented telescope in a very efficient way. And yet, once we realized that the next big thing that we're going to launch into space is going to be segmented, we turned around and said, hey, we have one of those, it's just not flying. So I think part of the question to your answer is really to look into the details of how these facilities operate and not hold back in terms of investment of resources in trying to ask questions that might not be as obvious now, because we will gain time as we observe with these new telescopes to think of new questions. And to tie also into some of my work, you know, I've been looking how we can optimize CGI operations on Roman. I asked a very simple questions. Hey, why is the DM diversity that we use for the electric field estimation in our focal plane the one we picked, you know, 10, 15 years ago, and not the one that state-of-the-art facilities have been using over the 10 past years? I didn't know, you know, is it better to use the old version? Is it better to use the new one? We didn't have an answer at the time. We're slowly converging to one now. But I asked what I felt like was a very simple question, which in the end taught us a lot.
I think there's also the use of emerging technologies that can be used on these and tested on the 8 to 10 meter class telescopes that could later be implemented on the EELT, the GMT, so on and so forth. And you want to test it on those smaller observatories before you implement it on these extremely large telescopes, because the time on those extremely large telescopes is going to be incredibly expensive and valuable.
Hi, Maria Vincent from University of Hawaii. The one thing I thought I would hear more about, but didn't, unless I zoned out, was on starshades. How far along we are in making that a reality, and especially considering, you know, the scale of it and how it will be used. What is perhaps the most viable way of testing it using ground-based telescopes?
Yeah, Dan, I think you have the most experience with starshades.
So starshades have been tested on the ground in subscale, and that's the only way, in subscale experiments, that's the only way you can test it. You have to trust in the optical physics that it behaves as you predict, and then do a subscale experiment and validate it. So starshades have achieved arguably TRL 5 at the moment at flight Fresnel numbers. And going forward, I don't know that there's like predicted, there's a specific program anymore to develop them, but one of the very best cases for starshades would be in the UV. in which case the star shade can be smaller and more compact.
Do we have a question on that side of the room?
Hi, Jules Fowler from UC Santa Cruz. Kind of to the question of using our current 8 to 10 meter class as technology exploration for future extremely large telescopes. I guess as someone who is trying to do that, I do see a bit of tension between working on kind of these cool, exciting new experiments and keeping our facilities stable and able to continuously observe. So I guess I'd love your take on how to appropriately strike that balance.
Yeah, maybe I can say something about this. So, well, first, of course, we need to realize that we currently have like a dozen 8-meter telescopes, and we go to two like 30, 40-meter class telescope, and of course, the whole community cannot be served by that. So, these 8-meter telescope will also remain very important for actual doing science. I can, for example, foresee that, I don't know, we think there may be a planet around a certain star. Then before we go to the ELT, we first try it with, for example, SPHERE or GPI, or we detect the planet, and then with SPHERE or GPI, we try to find the context in terms of the circumstellar disks and things like this. So I think it's very important to indeed strike this balance in what you can do in technology development. Because I think here you may be very inclined to say, okay, we just do technology development, but actual science observation will not be forgotten, of course.
I would also like to add something that ties back to something Bruce said earlier this week during his GPI talk, where he said that GPI, when it was in Gemini South, lost some opportunities in terms of observing time because the operator didn't feel compelled to go to the setup procedure. It sounds silly, but I think that is a very real problem that exists in way more than just GPI. And clearly, they identified it as something that they need to invest into because he said there will be changes for GPI 2 as they move to Gemini North. So while it might sound trivial, I think one of the things that should be addressed is really to not hesitate to invest in the chore tasks of making sure that we have certain standardizations between the group of people who are trying to do exciting new stuff and people who are trying to keep things in order. And those are not always the same type of people who are trying to communicate to each other. So investing in tools and standardization, I do think is going to be very important moving forward, exactly to enable both types of work.
Maybe to add to that, I also think that what we see currently is that we will just get a transition from that's similar that happened when we were starting to build the 8 and 10 meter class telescopes, where the 1 to 4 meter class telescopes were slowly changed into robotic survey telescopes for galaxy observations. So I guess for the VLTs and the 10 meter class telescopes will also probably move more towards these large survey telescopes. That is difficult to do with like your top of the line telescope. I also hear a very strong push from the community that we should build more ELTs.
I'll go with one last round of questions.
Hello, Bhavish Rajput from MPI up here. So going back to the comment from Sebastian on the GPUs, like we need GPUs. I think there are more aspects which we need from the industry sector, and that is also one thing which I don't know. I also kind of missed in Spirit of Leo, that we don't know, or like at least I don't know what are the other aspects we need from the industry, and do we need to have like conversations with the industry to have them built specifically for us, or do we need to invest, let's say, in the positions which enable bringing that industrial technology to the, for example, high contrast imaging community, let's say for building the habitable worlds in next 20 years, for example. So what's your take on that? I mean, because I've been seeing there have been positions opening for the students on both grad level and the postdoc level, where we have been trying to work on the, for example, the test beds and everything, to enabling this technology, but I'm not seeing this industrial aspect also, or do we even need that aspect? So what's your take?
So I think that we can use a lot of the work that industry is doing. For example, a lot of the photonics technology that we're now using is really driven by industry needs. We are really making a lot of use of telecommunication developments. I'm not quite sure how much we have given back to them. I think the thing that we have given back to them is photonic lanterns, because that was really an astronomical sort of, well, not discovery, but creation. But I think it's also difficult because we feel like we're a big community, but if you look in the economic output of astronomy, we're not that big. So most of the companies are looking more towards life science to earn money from, and not from astronomy.
There are opportunities for industry in astronomy as well. So like for Habitable Worlds Observatory, we just had this one call where 7 different industry teams, and that includes their teams. So it's not just an individual industry company, but academia and other small companies, maybe as subcontractors. They were just awarded quite a bit of money to help us advance technologies for Habitable Worlds Observatory. So we definitely do include that industry aspect in there and do encourage that, for sure.
All right, I think that's all the time we have. We do have a coffee break now, but don't leave yet. Dimitri does have a few words he wants to share, but while he comes up here, let's please thank the panelists.
So before we go on to our last coffee break, so I would like to call Karl Stapelfeld to say a few words about someone who's really special to us and our field. So there are not too many who can be field defining the way that person was. So I would like to say to call Karl here to say a few words about that person.
Great. So you know who you are. Okay, hi everyone. As you know, we're meeting here in Pasadena because there is a strong high contrast imaging activity here on campus, you know, at the observatories, up at JPL. And so you've met a bunch of technologists here who are made contributions, and we'd like you to meet one more technologist and scientist who has made contributions to our field here. You may have seen him walking around like a regular conference attendee, inconspicuous, with his poster about stabilization of low-order wavefronts for space-based high-contrast imaging. But that person is Dr. John Trauger from JPL, here in the audience. So just to make sure, especially for the early career people, John has been a founding member of our high contrast community here in Pasadena. Before that even, he in 1990 was the scientist at JPL in charge of building the Wide Field Planetary Camera 2 for the Hubble Space Telescope, along with the engineering team there. And he was surprised to see, as much as anyone, that the telescope wasn't ready to work when it got on orbit. But John brought the answer about how to modify that backup camera. He brought that to NASA headquarters right as the aberration was being announced. So the solution was known just as the problem went public. And John and his group went off and implemented that camera. It launched in 1993. And it was the main camera for the Hubble Space Telescope, fixing the aberration all the way up until 2002, the Wide Field Planetary Camera 2. So that's enough of an accomplishment just there. Later on, the advanced camera would have a short circuit, and Wide Field Planetary Camera 2 had to come to the rescue on orbit and operate the last 2 years up to the servicing mission. So John's instrument saved Hubble twice. But the reason we're bringing him to your attention today is that part of that camera had little actuators inside it to align the primary mirror correction of Hubble on the optics inside. And that got John into the actuator business and then deformable mirror business and running the Small Business Innovative Research Program with Zionetics Deformable Mirror Company. And John and others realized that this wavefront control could enable optical coronography to work in space at a time where the infrared interferometer version of a Planet Finder mission was ascendant. And so John did two things that were impactful to those of us, especially on the space side, of this room right now. One of them was in 2000 to submit a proposal to the Discovery Program, small telescope, that was called Eclipse. And this was a proposal for the first real proposal for a dedicated mission that was a small space telescope with wavefront control like we are imagining we're going to have in our future missions as early as this fall. And many other groups went and did the same, proposing missions like that. And so it raised the awareness across the community of the science that you could do with a modest size aperture, and that has become the Roman coronagraph instrument today. That thrust that he and others made at that time, but he was the first. His proposal in 2000 lost in the discovery competition. It was beaten by Kepler. Not such a terrible outcome. But like Kepler, when it lost, it got consolation prize money. And that money John used to start what we now call the high contrast imaging testbed at JPL. His group was a nucleus for many people to come together and work on this technology during TPF days. Dimitri and I were both in his group. I was in the 90s, Dimitri came in the 2000s. So that really helped bring together people and future generations of folks to go and develop the capabilities that we needed to get HWO now as a top priority. So I just thought you should all know who John is, what his contributions are, and that we are extremely proud of him here in the Pasadena community. So John, thank you very much for all that you've done. If you wanted to come up and say something, we'd be happy, but just I want people to know what you did and that you're here.
All right, I'm speechless, but and thank you for your kind words. That's really unexpected. But one thing, a number of things are illustrated here, and one is that there really is a through line in technology from Hubble and the correction of the aberration, which is wavefront control, and the pathway to the extreme precision wavefront control that we're going to need for HWO. Another lesson is that our opportunities to fly something new in space are very few, and we need to take advantage of them. HWO is our opportunity, but for it to be real and for it to happen, all the new ideas that have been presented and all the talent and youth that's in this room needs to be brought to bear in the next couple of years, or it's too late. The train leaves the station. To be ready for HWO, the new ideas have to be reduced to engineering reality. And so it's urgent. I hope that, the investments now appear to be possible to actually invest in the technologies, but it has to happen. It has to happen and become engineering reality in the next few years, or this generation will miss its opportunity. That's my message, and I think that's what we've learned.